இன்டர்வியூ எதாவது அட்டெண்ட் பண்ணீங்களா?
இல்ல சார். ட்ரை பண்ணிட்டு தான் இருக்கேன். எல்லாமே எக்ஸ்பீரியன்ஸ் தான் சார் கேட்குறாங்க. ஃப்ரெஷர் கேட்கவே மாட்றாங்க.
ஓகே. உங்களுக்கு முன்னாடி எக்ஸ்பீரியன்ஸ் இல்லையா?
அ
நீ ஃப்ரெஷரா நீங்க? வேற ஒரு கம்பெனில ஒர்க் பண்ணிட்டு
எக்ஸ்பீரியன்ஸ் வந்து
இருந்தீங்கல்ல?
எனக்கு ஒரு 5 இயர்ஸ் எக்ஸ்பீரியன்ஸ் இருக்கு சார். ஆனா எம்பெடெட்ல எக்ஸ்பீரியன்ஸ் இல்ல சார்.
ஓகே.
பிஎல்சி அந்த
சரி.
மாரி. பிஎல்சி
அஜ்மல் நம்பர் இருக்கா உங்ககிட்ட?
நம்பர் இல்ல சார். நம்பர் இல்ல சார்.
சரி. நான் அஜ்மல் கிட்ட ஆக்சுவலி ஒண்ணு சொன்னேன். லைக் நீங்க
சரிங்க சார்.
பண்றதுல யூ கேன் கன்வெர்ட் தட் இன்டூ அன் எம்பெடெட் டொமைன். ஓகேவா?
ஓகே
இப்போ
சார்.
நீங்க என்ன
சரிங்க
டொமைன்ல
சார்.
ஒர்க் பண்ணிட்டு இருக்கீங்க ஆக்சுவலா?
இன்ஸ்ட்ருமென்டேஷன் சார். பிஎல்சி,
ஆ
டிசிஎஸ் அந்த மாரி
ஓகே. ஸோ பிஎல்சி
ஃபீல்டு
தானே
தான்.
விச் இஸ் குவைட் சிமிலர் டு எம்பெடெட்.
ஆமா சார்.
ஓகேவா? ஸோ யூ கேன் சே
எஸ் சார்.
யூ ஆர் ஒர்க்ட் இன் அன் எம்பெடெட் ப்ராஜெக்ட் அண்ட் யூ கேன் ஷோ தட் அஸ் அன்
எஸ் சார்.
எக்ஸ்பீரியன்ஸ். ஓகே. ஸோ நீங்க இங்க நிறைய
எஸ்.
ப்ராஜெக்ட்
ஓகே
சப்மிட்
சார்.
பண்ணியிருப்பீங்க. கரெக்ட்டா?
எஸ் சார்.
அந்த ப்ராஜெக்ட்ல ஒரு சிலது உங்களோட இண்டஸ்ட்ரி ப்ராஜெக்ட்டுக்கு ரிலேட் ஆச்சு அப்படின்னா, அதெல்லாம் நீங்க பண்ண ப்ராஜெக்ட்டா சொல்லிக்கலாம்.
ஓகே
ஓகே.
சார்.
சி
ஓகே சார்.
first round will be the HR round. Okay. So HR is the
எஸ்.
one who
ஓகே
is going
சார்.
to call you. Correcta?
ஓகே சார்.
So HR
எஸ் சார்.
doesn't
கரெக்ட்.
understand the technical points.
எஸ் சார்.
They have some list of things. They just need to know இதெல்லாம் நீங்க முடிச்சிருக்கீங்க, இதெல்லாம் நீங்க பண்ணியிருக்கீங்க, உங்களுக்கு எவ்வளோ எக்ஸ்பீரியன்ஸ் இருக்கா, அது மட்டும் தான் அவங்க செக் பண்ணுவாங்க. அது இருந்துச்சுன்னா
எஸ்
தே
சார்.
வில் தே வில் மேக் யூ டு திஸ் இன்டர்வியூ. ஓகேவா? ஸோ நீங்கள் ஹெச்ஆர் கிட்ட
எஸ்
இதெல்லாம்
சார்.
எக்ஸ்பிளைன் பண்ணீங்கன்னா அவங்களுக்கு புரியாது. அவங்களுக்கு தேவை நீங்கள் இதெல்லாம் பண்ணியிருக்கீங்களா இல்லையா, அவ்வளோதான். ஸோ டெல்
எஸ்
தெம்
சார்.
that you did this relevant experience in the embedded. Okay, once you get into this technical part, you can explain this. இதெல்லாம் நான் பண்ணியிருக்கேன் அப்படின்றத. They will understand.
ஓகே சார்.
ஓகேவா?
எஸ்
நீங்க
சார்.
ஹெச்ஆர் கிட்ட இதெல்லாம் எக்ஸ்பிளைன் பண்ண அவசியம்
ஓகே
இல்லை.
சார்.
First get into an interview.
ஓகே
Okay,
சார்.
and then we will see
ஓகே
what
சார்.
happens.
எஸ் சார். ஓகே சார்.
Yeah.
அட்டன்
ஏன்னா நீங்க
பண்றேன்
ஒரு
சார்.
5 இயர்ஸ் எக்ஸ்பீரியன்ஸ் வச்சுட்டு அதை வேஸ்ட் பண்றீங்க. இப்போ நீங்க திருப்பி ஃப்ரெஷரா ஜாயின் பண்ணீங்கன்னா அந்த 5 வருஷம் வேஸ்ட் இல்ல.
ஆமா சார். ஆல்ரெடி இத ரிலேட் பண்ணி தான் சார் நான் ட்ரை பண்ணிருக்கேன். அவங்க
ம்.
இருந்தாலும் எம்பெடெட்ல என்ன ஒர்க் பண்ணிருக்கீங்க
ஆ
அப்படின்னு கேட்குறான் சார்.
அப்படின்னா
லிங்க்டின்ல இருந்து
நீங்க
கால்
வந்து
வருது.
நீங்க ப்ராஜெக்ட்ஸ் எல்லாம் உங்களோட ஐ மீன் ரெஸ்யூமேல கொஞ்சம் ப்ராப்பரா போட்டிருக்கணும். அந்த ப்ராஜெக்ட்ஸ் இப்போ நீங்க ஒர்க் பண்ற கம்பெனில பண்ண மாதிரி காட்டணும், அவ்வளவுதான்.
ஓகே சார்.
ஓகேவா?
நான் மாடிஃபை பண்ணி ட்ரை பண்றேன் சார்.
ம் சரி. ஓகே.
ஓகே, ஓகே.
அஜ்மல் கிட்ட சொல்லியிருக்கேன் ஐடியா. அஜ்மலும் அந்த மாதிரி தான் ட்ரை பண்ணிட்டு
சரிங்க.
இருக்காரு. ஓகேவா?
ஓகே
நீங்க
சார்.
அஜ்மல் கிட்ட வேணா பேசி
சரிங்க.
பாருங்க. ம்.
சரி. ஓகே, ஓகே சார்.
ஓகே.
நம்பர் மட்டும் கொஞ்சம் சென்ட் பண்ணுங்க சார்.
ஓகே. நான் வாட்ஸ்அப்ல அனுப்பிச்சு விடுறேன்.
ஆ, 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 ஓகே சார்.
ஹை நீலம். குட் ஈவினிங்.
Hi, sir. Good evening.
Yeah. So they made you join earlier.
Yes.
Okay, okay. So how is everything? You'll be joining on Wednesday, right?
Yes, sir. All's good.
Okay. Yeah. Hi, Yuvraj.
Hi, sir.
Yuvraj, அந்த C++ ரெக்கார்டிங் அமிச்சு இல்லையா?
பார்த்துட்டேன் சார். போயிட்டு இருக்கு
ஓகேவா?
சார்.
ஓகே.
ஓகே.
If there is any doubt, let me know.
ஓகே சார்.
ஓகேவா? கிளியரா இருக்கா?
கிளியரா இருக்கு சார்.
ஓகே.
6 மாடியூல் 6 வீடியோ போயிட்டு இருக்கு. பேலன்ஸ் போயிட்டு இருக்கோம் சார்.
ஓகே, ஓகே.
Good evening, sir.
Good evening, Bala. So how was pick, Bala, Yuvraj?
Yes, sir. It's good, sir.
Okay. You haven't done project in C++ and PIC, right? Only C project you have did,
Yes, sir.
correct?
Yes, sir.
Okay, I will explain C++ project and PIC project by tomorrow or day after tomorrow. Okay, so start working on that.
Okay, sir.
Yeah. Yeah, okay. We will start. Good evening, guys.
Good evening, sir.
Good evening,
Yeah.
sir.
Yes. Okay. So from today we will start a new module. Okay, which is an device driver for ARM architecture. Okay. So far for the current batch, we have completed 3 modules. Okay, C++, and bare metal programming and PIC microcontroller. Okay, so these 3 are like an basics to you people. Okay, like hereafter we will be seeing a multiple modules. In those modules it will be something like in 32-bit microcontrollers we will dealing an specific automotive application like RTOS. Okay, and then we will see the IoT. Okay, then Linux device driver, all these things. Okay, so these 3 so far what you have learned is the basic. We'll be using the C program for all these programs. Okay, like in your RTOS, we'll be using a C syntax. In the device driver, we'll be using a C syntax. So C is a base for all these things, right? And other people who are joined in this session are those who have already completed the diploma program. Okay. The reason why I asked you people to join in this session is like some of our students are attended the interviews. Okay, they asked the questions from the device driver. Okay, since you mentioned STM32 in your resume, okay, so they will be asking a questions from the STM32, which is a device driver, how to write a driver program for this STM32. That is what the question they will ask. Okay, since you don't know about that, because you have only studied the RTOS on ARM, we didn't much discuss about the ARM architecture and how to write a driver for ARM in our previous module. Okay, so we have included this module for the new batch. Okay, so that's why I asked you people to join in this one, right? So get trained with this. Can you share me the meeting link? Okay. Can anyone share the meeting link to Mohammed in the group? Meeting info. Okay. So that is the reason I asked the other students who have already completed this module also to join in this one. Okay. This module is for both the device driver as well as an RTOS. Since you people already learned this RTOS, if you want, you can stay after this device driver module for the RTOS again. Okay. Or just learn this device driver fully and practice with the board. Okay. And I hope Vijay have posted the multiple links in your group for purchasing this device driver STM board. Okay, I hope you people have purchased. If not, kindly purchase it because we'll be using that board for both device driver as well as an artist. Okay, it will be around somewhere some 1,200 to 1,400 rupees per board. Okay, so kindly get it. It will be very useful for you since it is an ARM architecture 32-bit microcontroller. It will be very useful for you. Okay, so we'll get into this class. So this first session or first day of this class will be mostly about uh, the basics of ARM architecture and the basic of STM. And I'll tell you what software we are going to use, and that is what IDE we are going to use, how to download and install all these things. Okay, so that is what we are going to see in today's class. So just let me know is my screen visible for you people. Is my screen visible?
Visible, sir.
Okay. Yeah, so this one is the PPT for a device driver and serial communication protocol. Okay. Right. Okay. So those who already joined my class, people might have know that I'm not a big fan of a PPT. Okay, so let it there. Okay, so this one is for the device driver. Okay, so here what we are going to do is we are going to use an ARM Cortex board. Okay, so can anyone tell me what is ARM? ARM, ARM. Any idea? You people might have learned about ARM or heard the name ARM architecture or ARM processor, something like that, right? What is ARM or where you have learned that name? ARM.
Application related microcontroller.
Application related microcontroller. Okay. Any other thing? Okay, you people are using your smartphone, right? Whatever the phone it is, what architecture it is, or what processor you are using. Any idea?
So related to MediaTek and Dimensity.
Okay, so you'll be either
Snapdragon.
using you'll be either using an MediaTek or you'll be using the Snapdragon. Okay, both these softwares are based off the ARM architecture. Okay, also the Apple's M4, M3, M2, M1 chips. Okay, we have this M series chips, right? All these chips are, or they have some other chips like an A15, A16, A14. Okay, those chips are again an ARM architecture. Okay, so everything apart from what you are using in the Windows, okay, everything else is an ARM architecture. And Windows last year they have announced they are planning to switch to an ARM based microprocessor. Okay, Windows has a specific architecture that is an x86 architecture. Okay, only this Microsoft is having a different architecture that is an x86 architecture, which is nothing but in 32-bit. Okay, even though they moved to 64-bit, they're still calling it as an x86 architecture. Okay, and then we have an ARM architecture. So Windows is planning to switch from this x86 architecture to ARM since it has an higher battery power. Okay, and all these things. I will explain all these things why this ARM has an higher battery power and all these things. First of all, ARM architecture. Okay, so ARM. ARM is nothing but it is an
Advanced risk machine.
yes. So ARM is nothing but it is an advanced risk machine, RISC machine. And this RISC is nothing but this risk is reduced instruction set computer. Okay, so ARM is a specific advanced risk machine architecture. Okay, and risk means it is a reduced instruction set computer. Like in our standard instruction set, we have something like some of the instructions will be reduced in order to achieve the more calculation speed. Okay, so that is what a risk is. ARM is nothing but it is something like they are actually manufacturer of an 32-bit as well as a 64-bit. So all your mobile phones, your laptops, this iPad, Okay, your Mac and everything is in 64-bit, and the microcontroller specific boards are all 32 bits. Okay, we will discuss that one. So they are 32-bit and 64-bit, not a manufacturer. Do you know who ARM is? They are not the manufacturers. Do you know who ARM is? Okay, so all the boards you are seeing, they are not actually manufacturing that board. Okay, they are just giving the blueprint of that architecture to whatever the company they want. Okay, for example, if it is an Apple, they will design that architecture and they will sell it. Okay, we call that as an IP. Okay, intellectual property. So they sell that intellectual property, that is that architecture, to the Apple, or they sell it to the Snapdragon, or they sell it to this MediaTek. Okay. Now what they will do is they will just design that, or they will just alter this architecture like however they want, and they will just manufacture on their own. Okay. So ARM, they are actually getting some, like millions of money by just sharing the blueprint. Okay, that is nothing but some extension file. Okay, for just sharing that file, they are just getting some millions and millions of money. Okay, so ARM is not a manufacturer, they are just sharing the blueprint. Okay, they are just a designer, that's all. Okay, in simple words, we'll be calling that as a designer. Okay, so they are the leading. Okay, either a microcontrollers or microprocessor designers. Okay, so nowadays most of the companies starts from the modern embedded systems like smartphones, automotive ECUs, your Internet of Things, IoT protocols, industrial robotics. Everything is using this ARM protocol only, or ARM architecture only. Okay, so why everyone is going to this ARM architecture? This was a question. As I already said, Windows, they have that own architecture, even though they are planning to switch to this ARM architecture from mostly 2026 or 27. Okay, why is there are many reasons for why everyone is switching to this ARM architecture. And you might have heard that this your mobile phones have an higher battery as compared to your Windows laptop. Okay, have you noticed that? Okay, that is, it is a low power consumption. Okay, now why it is low power consumption? That is a question. It is again in processor as like your Intel or something. Okay, why our Intel or AMD is actually an x86 processor only for your no. Okay, so Intel and everything is using this x86, that is it, because they are using this Windows for their PCs and everything. Okay, now why it is a low power consumption means in your mobile phones or laptops, you might have heard something called as a quad core, octa core processor. What is meant by quad core? What is meant by octa core?
Quad core means four different controllers clubbed together, and octa core means eight core will be there clubbed together.
Okay, is it in controller or processor?
It's a controller.
Okay, what is the difference between controller and processor?
Processor means it will be doing only that arithmetic operations or any particular jobs. Controller means it with the peripherals it will be available. So altogether it is a controller.
Okay, now tell me your mobile phone has a controller or processor?
Processor.
Okay, so if it is on core, the core will be controller or processors.
Processor.
Okay, okay, as simple as that. Because your mobile phone is not going to control anything. Control in the sense it will not do any physical task. Okay, like if you are ordering any food from your mobile, okay, that can be done, but your mobile will not prepare your food for you. Okay, so that is what the difference between controlling and processing. Okay, controlling, it will do only the calculations and everything. Processor will only do the calculations and everything, whereas controlling, it will do the physical activity. Okay. What we are, yeah, the cores. Okay, for example, if it is an quad core, we'll be having a 4 different cores. Let's assume this huge box is a processor. Okay, inside this processor, we'll be having a different cores. Core 0, core 1, core 2, and core 3. Okay, so this is my core 0, this is my core 1, this is my core 2, and this is my core 3. Okay, now if you want to calculate anything, there will be for example, let's say if you want to calculate some 4 different processor at a time. Okay, each and every core will be doing that, so 4 different processor at a time. Okay, the parallel processing is very fast since it has a multiple cores as compared to the single core. Okay, and also if you are working on any particular application, let's assume only this core 0 is operating, then we can actually turn off, or there is something called as a low power mode. Okay, we can make this C1, C2, and C3 in the low power mode. Okay, so this 3 will not consume much power. Okay, only this core 0 will process all this limited tasks, whatever. For example, if you are just chatting in the mobile phone, if you're not doing anything else, okay, let's assume that is only one core is enough for that. All other cores will be in the turn off mode. Okay, so we can actually able to preserve the power, or we can able to distribute the power to each and every course, depends upon the application. Okay, core 0 might be an intense application, or core 3 might require a low power. Okay, so we can able to allocate the power, so we can able to redistribute it, so it is an low power consumption. That is the first thing. And second thing is, it is an high performance, as I already said, since we have a multiple cores. Okay, so it is an high performance with respect to its size and cost. Okay, and there is something called as a scalable. Okay, your M1, M2, M3, M4, all these 4 processors are same processor, but we can easily able to scale it. It depends upon how much performance we want, or how much cores we require, how much processor it has to do. We can actually able to scale easily in ARM architecture rather than compared to this x86 architecture. Okay, and we can actually able to use it for the real-time purpose. Okay, so there is a board that is specifically designed for a real-time operating system. I will explain in a moment. Okay, so there are multiple advantages over there, right? So ARM is having 3 different types of boards: A, R, M. Okay, so they are actually having 3 different types of board, or they will just design 3 different types of board. One is A series. Okay, the next one is R series. The next one is M series. Okay, so there are 3 different series of boards will be there, right? So A series is an application oriented. That is what an A stands for. That is your laptops, your mobile phones, or any digital processing devices, your camera devices, everything will be having an A series. Okay, wherever you're going to run multiple applications in a single board or a single chip, there they will use an A series. All your, that's what your Apple is actually, this A16, A15, A14. Okay, that is actually nothing but an A series of ARM architecture, right? Similarly, this M architecture, all these things are using an A series boards only, since it is an high speed. Okay, and it is very costly as compared to R and M, right? So it is an application oriented. Uh, R series is nothing but it is in real time boards. Okay, so in our microcontrollers, if any boards or any application which requires a real time system, okay, like your car ECUs, okay, and your missile control systems or any defense related boards, okay, everything will have this R series of ARM architectures. Okay, so it is specifically made to deal with in real time applications where time, or I will just say it is in time constrained applications. Okay, if anything that want to be completed within that given time period, we call that as a time constrained applications. Okay, so this R series is specifically made for this real time application. And the last one is an M series. This is for the microcontrollers. Okay, it is a low power, low memory device and also low cost. Okay, so we'll be using this M series only because since it is a microcontrollers, it is for a simpler applications. If you don't have a much memory requirement or much no application oriented, then we'll be using this M series architecture. Okay, so this is how this ARM manufacturers are splitted, their application based designs. Okay, A series is only for the high-end processors, R series is only for the real-time purposes, and M series is only for the microcontrollers. Okay, now based on these things, ARM is actually having multiple versions. Okay, start with ARM version 1 to ARM version 9. Okay, so the recent version is ARM version 9. So ARM version 1 is actually designed on the year of 1985. Okay, so that is what the first ARM 32-bit RISC architecture was developed. Okay, then in ARM version 2 they added multiple instructions. Okay, and ARM version 3 they added some multiplication instructions. um, ARM version 4 they have added something called as, okay, this I will explain in a moment. ARM version 4 they added something called as a thumb instruction. This is one of the very important thing in the ARM architecture. Okay, thumb instruction. We will discuss about this in a moment. Okay, then in ARM version 5, I'll just write all these things. Okay, version 5 they actually implemented the digital signal processing, improved digital signal processing. Okay, and version 6, version 7, 8, and this latest version is version 9. Okay, so this is specifically made for this AI ML processing. Okay, so it is developed in the year of 2021 to something. Okay, this range they actually developed this board version 9. Okay, the current version is an ARM version 9. Okay, and mostly we'll be using this three things. This ARM A, R, and M. They are actually comes with the ARM version 7 series only. Okay, in ARM version 7 only they are actually implemented this A, R, and M modes. Okay, now in this we'll be using, as I already said. Okay, so far is it clear? Any doubts?
Sir.
Yeah.
What is the difference between a normal processor and a DSP processor? DSP.
Okay, DSP processor, it is specifically made for processing the digital signals. Okay, like your image processing, your digital image, if you want to convert into bits and process it, there this digital signal processing will come. Okay, or if you want to split your digital signals, or if you want to convert this analog signals and quantize into a digital processing for your board, okay, there this digital signal processing will come. Your normal processor, it can do all these things. Okay, it is capable to do all these digital conversions and all these things, but it will take more time, and also it will actually make more strain on your processor. Okay, during this conversion your processor will not do any other operation. Okay, So that's where this digital signal processing comes. It is a specific controller which is available to deal only the signal processing things. Okay, so your processor will work independently, your DSP will work independently, and only this conversion result will be sent to your microprocessor for the calculations. Clear?
Yes, sir. Sir, using C programming only we can code on DSP also.
Yeah, we can do that. C syntax is used for DSP also.
Yes, sir.
Okay.
Yes, sir.
Yeah. Okay. Yeah. Any other doubts? Is it clear till now?
Yes.
Now we are going to use STM F like that series we have mentioned now in the group.
Yeah.
And
I'll
that,
tell.
and that
I'll tell where it is comes.
okay.
Okay. Yeah. Okay. So as I already said, we are going to use this M series only. Okay. So M series is a microcontroller based architecture, right? Okay. So this all these A series, R series, M series are, we call it as an ARM Cortex A series, ARM Cortex R series, ARM Cortex M series. Okay. So now this M series is again classified into multiple divisions. Okay, depends on what kind of things you are going to do, right? So this first one is Cortex M0 or M0 plus. Okay, so this is the first model they have introduced in the microcontroller area. Okay, so this is an ultra low power basic operations. Okay, we have an online simulator for this STM board. Okay, we have something called as an OKV. Okay, so in this OKV we have an STM board which is nothing but an C0. Okay, which is STM 32C0 board. Okay, this C0 board is actually in Cortex M0 architecture only. Okay, it is a very low power and basic operation, and we can actually run our program in this OKV also. But since it is a basic operation, we couldn't be able to perform the communication protocols and all these things very efficiently. Okay, so that's why Vijay asked you to buy the board for this one. Okay, and also we can't able to do the RTOS in the C0 board. We already tried with the previous batch, but it is not working properly. Okay. The next one is, so this is M0, M0 plus is an ultra low power and it is developed for the basic operations only. Okay. And the next one is Cortex M3. Okay. So Cortex M3, they have actually implemented this DSP in M3 only. Okay. It is I won't say it is an ultra power or good power. It is actually an balanced power. Balanced power to performance ratio. Okay. So here they have introduced something called as a digital signal processing. Okay. So sorry. For M4 only they have introduced. Okay. Here they have introduced something called as an FPU. Okay. FPU is nothing but it is a floating point unit. As like I said to Aparna about this DSP. DSP is an digital signal processing. We have a specific controller for processing the digital signals. Okay, similarly FPU is nothing but it's a floating point unit. Okay, if your microcontroller has a floating point unit, that means it has a specific uh, area there it can calculate this floating points, that is decimal points. Okay, because the decimal point conversion is very, very difficult for your controller or a processor. Okay, in order to do these calculations, it will take more time. Now, for that, they have introduced something called as an FPU, floating point unit. If your board doesn't have a floating point unit, it will be mentioned in the data sheet itself. Okay, I will show you the data sheet in a moment. Okay, it will be mentioned in the data sheet itself that it is an FPU enabled. That means your microcontroller as an capable of handling the floating points or decimal values. Okay, that is what this FPU is. So FPU is only introduced in the Cortex M3. In M0 board, you can't able to perform this floating point very efficiently. Okay, so in Cortex M4, on top of this FPU, they have introduced the digital signal processing. Okay, plus we have an FPU also here. Okay, so this is Cortex M4, and the board which I sent in the group your STM32 F446 or your STM32 F 334 or your STM32 F401. Okay, all these boards are Cortex M4 series only. Okay, since it has a digital signal processing and the FPU will be using this board very often. Okay, you can get any one of this board. It is not always required to use only this 446 which is given in the group. Okay, if this is out of stock, if you have this F334 or F401, you can get that also. Okay, or you can get any Cortex M4 STM board. Okay, so that is fine. Just search Cortex M4 STM boards. If you have anything, any boards which is falls under this Cortex M4, you can get that one. All these things are same for this particular series. The only difference is in your code generation part in STM IDE. Okay, you need to select this particular board. That is the only difference. Everything else is same. Okay, so this is Cortex M4, and the next one is Cortex M7. Okay, this is an high performance board. Plus it has an advanced DSP. Okay, so this is Cortex M7, and the next one is Cortex A/R. So as I already said, this one, this A/R. Okay, so that is the next one. We'll be having this applications or real-time processor. Okay, so that is what this Cortex AR. So in M series, we have only these four different series. Okay, four different models: M0 or M0 plus, M3, M4, and M7. Here we'll be using this M4, which is for us, it is more than enough. Okay, so it has an DSP, it has an FPU. Okay, and we have multiple communication protocols here. We have a timers. Okay, all these things I will explain that in a moment. Okay, we have everything over here, and not only the STM board, this Cortex M4 will be having the Philips NXP board. Okay, that is LPC boards. All these LPC boards will be having this Cortex M4. Then we have STM32 boards, and we have a Texas Instrument TI boards. Okay, so most of the C series boards are Cortex M4 only. Okay, and apart from that, I think we are having one Atmega board, Atmel Corporation's board. I'm not sure the series name, but it is also having an ARM Cortex M4 series. Okay, so this Atmel series. So these are the different manufacturers. The same thing, Cortex M4 is an architecture. Again, this ARM will be this Cortex M4 architecture diagram will be given to all these manufacturers. They will manufacture their board on their own. Okay, so that is the only difference. Okay, so this is an simple introduction to the ARM series. Okay, any doubt so far?
Sir,
Yeah.
this STM32 NXP and TIC series Atmel, if they all have the same features, how do we decide which board to select for what application?
Okay. As I already said, they will not exactly manufacture that same architecture. Okay. For example, if you take this STM32, this 446 is an Cortex M. 334 is also a Cortex M4. 401 is also a Cortex M4. But the RAM size, flash memory size, as well as how many peripherals are there, like how many timers, how many bits of ADC, okay, and how many protocols are there, communication protocol peripherals are there. That will be different for these three boards. Okay, let's say your board requires or your application requires three different SPI protocol or SPI communication. Okay, your 334 board, it has only two SPIs. Okay, then you will not select this board. Okay, so depends on the application, like how much pin I'm going to use, or these 4 architecture, the pins will also be varying. Okay, it's not a constant same 60 pins will be available for all these 4 boards. Okay, it will be differ based on the architecture, based on the manufacturers. Okay, and based on the applications. So you'll be selecting the board based on what application you are going to use, what are the peripherals you are going to use, how much memory you are going to require, how many pins you are going to use. Okay, so these 4 things will matter for deciding which board you are going to use. Okay.
Yes, sir.
Yeah. So clear so far? Any doubts in this ARM basics? Shall we go to next topic? Okay. So this is the same thing for the ARM Cortex RM, M0, M7, M4, everything. Okay. Yeah. I forgot about this thumb instruction. As I already said, this ARM version 4 is having something called as a thumb instruction. Okay, so this is very important in the ARM architecture. Thumb instruction is nothing but it's like, okay, for example, in your PC or a laptop, if your PC is an 64-bit architecture, okay, most of the nowadays, all this process are 64-bit architecture only. Okay, if your board is an 64-bit architecture, you can actually run 64-bit applications as well as 32-bit applications. Okay, both are possible. Okay, for example, I'll show you. So my PC is an 64-bit architecture. Okay, you can see there are 2 program files over here. This program files is for the 64-bit. This program file is for the 32-bit. x86 is nothing but it's a 32-bit. Okay, if I open this, all these programs over here are running in the 64-bit, and all these programs which are installed over here are running in the 32-bit. Okay, a single architecture can switch, either it can run in the 32-bit or a 64-bit. Okay, similarly, your microcontroller here is a 32-bit microcontroller. Okay, your ARM processor and all these things are 32-bit microcontrollers. That means you can actually able to use 32-bit registers or 32-bit registers or instructions. Okay, also if you want, you can use an 16-bit instructions also. Okay, you will be enabling the thumb mode in the ARM Cortex series. Okay, in that thumb mode, you can actually able to use a 16-bit instruction in a 32-bit architecture. That is possible. Okay, so that is what called as a thumb instructions. So it is not always, if you want to run a 16-bit instruction, you need a 16-bit microcontroller. That is not a thing. Okay, by using this thumb, you can actually able to run the lower versions of instructions also. Okay, so that is possible with this thumb instruction, right? Okay, so that is an it has an thumb 2 architecture. Okay, so the next one is, so these are the applications of Cortex M4 processor and the architecture. Okay, I will show the architecture separately in the data sheet. Okay, so this is for M3 architectures, right? Okay, there are some core peripherals of the Cortex M3 as well as Cortex M4. These four things are very important. Okay, is my screen visible? This PPT screen?
Yes, sir.
Okay. Now, there are four core peripherals available in the Cortex M3 as well as Cortex M4. Okay, M4 is nothing but it is an, DSP enabled M3. That's what an M4 is. Okay, so M4, everything else is same as the M3. Only thing is they added the DSP in the M4 architecture. That is the only difference. Okay, first one is system tick. Second one is system control. Third one is NVIC, nested vector interrupt controller, and fourth one is memory protection unit. These four are the core peripherals of your Cortex M3 or M4 series. Okay, we'll see one by one what this was. First one is a system tick. System tick means it is a 24-bit countdown timer. Okay, for example, if you are using a real-time operating system, as some of you already studied this real-time operating system, there we can't actually able to use the delay mode or timer mode. Okay, we have a specific timer mode for the RTOS. Okay, specific delay mode for the RTOS, right? So there we can't able to use the regular timer from your architecture. Okay, but this Cortex M3 or M4 series, what it will do is it will actually make you use the system tick as an timer. Okay, you can enable the system tick for a timer and you can able to use this for your internal calculations in the RTOS. Okay, so your RTOS will take the system tick as an input and it will process the time period based on this. Okay, so it is a 24-bit countdown timer. That means it has a 2 power 24 times of values. Okay, that much amount of value. From that to 0, it will just count down. Okay, so this is one of the most important core peripheral available in the Cortex M3 and M4. And the second one is there is a nested vector interrupt controller. Okay, now the question is, you people have already studied this PIC microcontroller and all these things, right? What is interrupt?
To delay or giving the delay in between some processes running, we are hold it and we are running another process within a particular time.
Okay, we are holding the process. Okay, can anyone give more specific
Here to
definition?
enable the interrupt flag.
Execution of high priority task.
Okay.
When the controller is executing some task, in between any high priority task comes, the controller will execute the high priority task and it will switch back to the old task again.
Okay. Okay. But
we are using the counter and the timer flag to to use the interrupt.
Okay. So Arvind, you have studied PIC, right? What are the different interrupts available in PIC?
Like
ADC.
as I am aware of.
Apan, I'll just ask. Arvind, I'll come back to you. Okay. Yeah.
Yeah.
Okay, Arvind. Sorry, Aparna.
Yeah. What I can say?
Okay.
Sorry.
Okay, no issues.
Yeah.
Yeah, Panna. Now you can carry on.
Analog to digital converter,
Okay.
UART.
Okay.
I2C.
Okay. What are the major classifications? Okay, these things are using interrupts. Okay, fine. What are the major classifications of interrupts?
Software and hardware.
Okay, one is an hardware or external interrupt, software interrupt. Okay, in software interrupt,
Yeah.
we'll be
No,
having.
we are giving the loop. I mean counter. We give some counter delay. That
Okay.
is a software. Yeah.
Okay.
Interrupt. Like in the program itself, we are giving that is a software internally, or externally we are using some hardware, or externally we are getting input and we are giving that delay. Mean that is external.
Okay. So interrupts.
Hardware.
Yeah, interrupts we will be having an external
peripheral and a timer.
Yes, good. So we have an external, we have a peripheral. Then what is the next one?
Timer.
Yeah. So we'll be having a timer interrupt. Okay, this peripheral and timer interrupt is actually what we call it as in software interrupts. Okay, so this is nothing but your hardware. An external hardware pin will be using to trigger the interrupt. Okay, now what does interrupt means? Interrupt is a mechanism where your microcontroller temporarily, I won't say stop, microcontroller will temporarily pass the current execution program. Okay, and it will go to the high priority event. It will execute and it will again come back to wherever it is passed. Okay, it will resume from wherever it is passed. Okay, that is what an interrupt is. So interrupt, your microcontroller temporarily pass whatever it is executing. Okay, it will attend that particular task and it is again coming back and it will enable that one. Okay, so my interrupts will be using in many different things, right? Here, um, in your peak microcontroller, you have only this external peripheral timers and all these things, right? But here in this Cortex M3 and M4, or in general, the ARM will be having something called as a nested vector interrupt controller. Okay. Now, first I will just split this into multiple things. First one is a nested. Second one is it is a vector. Okay, and we have an interrupt controller. So this interrupt controller we already know. So there is a specific controller, okay, for the interrupt. That is what an interrupt controller is. Okay, inside this Cortex M3 we'll be having an controller that is only dedicatedly available for interrupt processing. Okay, now what is meant by this vector and what is meant by this nested is vector means we'll be having something called as a table kind of thing. Okay, let's say this is my interrupt number 0. This is my interrupt number 1. This is my interrupt number 2. Okay, so each and every interrupt will have its own corresponding memory address. If this interrupt 0 comes, which address it has to go? If interrupts 1 comes, which address it has to go? Okay, it will be like in the table format. So you might have studied about this in the C program. Your switch case is actually faster than your if else. Okay, why? Because switch case is actually using the table format. Okay, if it is case 1, it will directly go and execute it. If it is case 4, it will directly go and execute. It is like in a table format. Okay, similarly, since it is in the table format, it will directly go to that particular interrupt
Virtual
value.
table kind of.
It is a vector table.
Okay.
Okay, so it will directly go to that particular table or particular value and it will just fetch that address and it will directly go. So as compared to the regular interrupt, your vector interrupt is much faster. Okay, so that is what an vector interrupt controller. So a specific controller, it will only do all this operation. It will directly go to that vector, that interrupt, it will fetch that address, it will directly go there. It will execute whatever the program inside that address. Okay, so that is an vector interrupt controller. Now what is mean by the nested vector interrupt controller is your interrupt will have another interrupt. Okay, for example, you can actually able to allocate okay, just a minute, I'll minimize this. Okay, now what is meant by this nested means, for example, let's say my interrupt itself has, what is meant by interrupt, it has, if it is any high priority task comes, your main program will be paused. Okay, and this interrupt will be executing, right? Now nested interrupt means your interrupt itself will have a priority. Let's say my interrupt 0 has an highest priority, okay, as compared to something like an interrupt number 10. Okay, so this has something like, let's say, low priority. Okay, now initially I am executing this interrupt number 10. I am calling this interrupt number 10. It is going to this memory address. It is executing. Let's say it has some 10 lines of code. Okay, it is executing. While it is executing in the fourth line, I am giving this interrupt number 0. Now what will happen? Since this has an highest priority, okay, we are currently inside this interrupt subroutine, but even though if this high priority interrupt comes, it will just pass here, it will go and attend this high priority. Okay, it will start executing its own subroutine. Once it is finished, it will come back and execute the fifth program. After completion of the 10th program, it will go to this main.c. Okay, so it is as like your main program and interrupt, but your interrupt itself has some priorities. Okay, so that is what called as a nested vector interrupt controller. So interrupt controller is having a vector table. Inside this vector table, your interrupts will have its own priority. So if any low priority interrupt is executing and high priority interrupt comes, means it will go and attend this high priority interrupt and it will again come back to this low priority. Okay, so that is that much amount of powerful your Cortex M series board is. Okay, clear this NVIC, because we'll be mostly using this NVIC in our RTOS. Okay, so that you should know about what this NVIC is. Okay, any doubts in this?
Is there any certain limit for this nesting? Nesting.
So it is actually ranging from 0 to 255. The priorities I'm saying, the priority value you can actually able to give from 0 to 255, but the interrupt, how many interrupts you can actually able to give us what differs from your each and every cortexes. I think here in this Cortex M3 series you will be using something like 2048 different interrupts. Okay, that much amount of interrupts it can allow, but you can give 0 to 255 priorities. Okay, 0 as the highest priority, 255 is the lowest priority.
One full 8-bit actually.
Yeah, full 8-bit.
Yeah. Okay.
Okay, so that is what called as an NVIC. So it is one of the again and core peripheral of your Cortex M3 series. Okay, and the next one is there is something called as an SCB. Okay, system control block. Just a minute. Sorry. So this system control block, it is something like, let's say, a guidelines to your controller. Okay, let's assume we have something called as a data sheet available for your microcontroller itself. Okay, if anything your microcontroller requires, it will be listed in the system control block. Okay, so your system controller block will have the interrupt priorities, as already said in this NVIC. Interrupt priorities will be stored in this SCB, as well as if there is any fault occurs in your microcontroller, that will be stored here. Okay, your fault exceptions, your system reset. Okay, where it has to go, that system reset will be available. Okay, it has all the informations about your microcontroller, as well as if there is any problem occurs in your microcontroller, that will be stored in the SCB. Okay, it is something like a reporting system or management system. Let's assume like that. Okay, it will manage everything. If there is any problem occurs, it will report it as a log, and you can easily able to go there and see what has happened in your microcontroller. Okay, so that is what an system control block is. Okay, and the next one is the last one. It is an memory production unit. So your memory production unit, let's say the example for this memory production unit is okay, let's say you are storing a value in any particular memory. Okay, so we have something called as an volatile and non-volatile memory, right? Okay, so if you stored a particular value in some memory addresses, and if there is any problem occur, let's assume there is some power surge occurs and some portion of your memory is corrupted. Okay, and let's assume you have some 256 bits of values. Okay, in that only something like an 24-bit or 32-bit is corrupted. Okay, remaining values will be there. Okay, but if you want to take this 32-bit of memory or 32-bit of value, you couldn't able to take that one. Okay, that is very difficult because the 8-bit of that is corrupted, right? Let's say I'll just write it on. Okay, so let's say this is my 32-bit. In that a particular 8-bit is corrupted, you can't actually able to fetch the entire value over here. Okay, so now in order to prevent that, what will happen is your MPU will split your memory into 8 different regions. 1, 2, 3, 4, 5, 6, 7, 8. Okay, your memory, your entire memory into 8 different regions, and each and every regions will have its own power supply connections. I won't say connection, power supply boards. Okay, or power signals to that. Okay, if there is any power surge occurs or if there is any data read write problem occurs, only that specific memory will be faulted. Okay, you can actually able to fetch all these memories fine. Okay, since your memory is, as like already said, this octa-core or quad-core processor, your processor will be split into 4 or 8 different regions, right? Similarly, your memory will be split into 8 different memory regions. Okay, if there is any data corruption occurs in particular memory region, only that region will not be available for your data retrieve or storage. Okay, all other regions you can actually able to work it out. Okay, so that is what a memory production unit. If there is no memory production unit available, your entire memory will be in a single block. If there is any memory corruption occurs, you couldn't able to access your entire memory. Okay, so that is what happens without this MPU, right? So your Cortex M3 M4 series is actually having this memory production unit. Clear? So these are the 4 core peripherals of your Cortex M3. First one is a system tick. That means it has an 24-bit timer that will be specifically used for your real-time application. Then we have an NVIC, that is a nested vector interrupt controller. There we will be having an vector table inside this vector table, we will be having a priority based interrupts. Okay, and then we have a system control bus that will be having all the system informations available for the system configuration to system reporting. Everything is available in the SCB. And the last one is an MPU, that is a memory production unit. There we'll be having a memory region that will be distincted or separated into 8 different regions. Okay, so that it will protect each and every memory separately. Okay, so that these are the core peripherals of Cortex M3 and M4. Okay, clear? Any doubts in this peripherals?
No, sir.
Okay. So this one is M4 architecture. Okay, this is hardware, and there's Harvard and von Neumann architectures, right? You people might have studied about this earlier itself. I hope you know about this, and that's why I'm skipping it. If you want, I will explain it. Does anyone want what this Harvard and von Neumann architecture?
No, sir.
Okay. Okay, these are M4 architectures that I will explain with the architecture diagram. Is there anything? Okay, so here you can see your M4 architecture actually supports up to 240 different interrupts. Okay, so yeah, so that's what this NVIC is, and it is in 32-bit RISC architecture. It has a DSP that we already, it has an FP also. Okay, and load store architecture, this is fine. Instruction set, okay, that is, it has an thumb to architecture. Okay, that is means it is a mixture of a 16-bit and 32-bit instructions. We can actually able to execute 16-bit as well as a 32-bit. Okay. Okay, so this is architecture that I will explain with an architecture diagram separately. Power place. Okay, everything else is okay. We have something called as a clock signals. Okay, this is one of the most important thing in any microcontroller. Okay, even you might have studied in the PIC microcontroller that everything is associated with the clock pulse only. Okay, even your microcontroller has an internal clock of 20 megahertz in the PIC microcontroller. Okay, now here in this ARM, we'll be having something called as a reset and clock control. Okay, I'll explain what is reset and clock control. Before that, first know about what are the different clock sources available in this ARM Cortex. We have something called as an HSI, we have something called as an HSE and PLL. There are 3 different clocks available in the STM or ARM Cortex. Okay, HSI is nothing but it is an high speed internal clock. Okay, this high speed internal clock is available inside your board, or I will say inside your chip. Okay, it's not a board, it is chip. For example, if it is an ARM STM32 board, okay, we have something called as this microcontroller board, right? Or microcontroller chip, not a board, chip. Okay, this chip itself has an clock. Okay, that is what called as an HSI, high speed internal clock. Okay, now this chip, obviously you will place it in a board. Okay, inside this board only we'll be having some pins over there, and over here we'll be having something, some LEDs. Okay, some pins are over there, all these things. Okay, now this is what called as a board, this outer edge. This board is having an oscillator. Let's assume this is what our oscillator is. Okay, this we call it as an high speed external oscillator. Okay, this chip, whatever the clock available inside this chip, we call it as an internal clock, and this outer board we call that as an external clock. Okay, and then we have something called as an PLL, which is nothing but phase lock loop. Okay, this is nothing but it is an software method of multiplying or dividing your HSI and HSC. Okay, if you want to increase the clock, you can do that in software. Okay, or if you want to divide the clock, that also possible with this PL. Okay, so this is a software method of increasing your clock frequency. Okay, for example, if you want to increase this 8 megahertz internal clock frequency to 64 megahertz, okay, you can use that by using this VLL. Okay, depends upon your application. If you want to increase or decrease your clock frequency, you can done that with PLL method. Okay, so we'll see one by one what this HSI is. So apart from that, we have something called as an LSI and LSE. LSI is a low speed internal and LSE is a low speed external. Okay, some of the board doesn't have this LSE. We will see that what board we are using and all these things. Okay, right. So okay, so we have this HSE oscillator clock, HSI and PLL clock. First one is HSI. HSI is an high speed internal clock. Here in your STM board, we'll be having an 8 megahertz of internal clock. Okay, so HSI is an high speed internal. It is an RC oscillator, which is present inside this microcontroller unit. And sources, it is an internally generated. Okay, it doesn't have any external source and all. Internally, it will be generating something like an 8 megahertz of oscillator frequency. Okay, uses, we can directly use the system clock for some peripherals, or we can divide it and use it for the VLL inputs. Okay, so that is possible. And purposes, we can use it for the power on reset. Okay, and system resets, whatever present or whatever operation you are going to do internally with your board, that can be done with this HSI. That can be done with your HSI. Okay, and how will you enable? You are enabled to this code. Okay, you can actually code this and you can turn on this HSI. Okay, so that is HSI, and HSE is an high speed external clock. I will show this in the STM IDE. Okay, how to configure and all this thing, that will be easy to understand. Since it has an graphical user interface, you can actually able to select each and every clock, how much clock I required, all these things in the STM IDE. Okay, that I will explain in a bit. So HSE is an high speed external clock, and we'll be connecting an crystal oscillator externally to the microcontroller that is inside your board. That will work as an external clock for that. Okay, so it can be a crystal oscillator or a ceramic resonator. Okay, whatever it is. And some of the nuclear board doesn't have an high speed external ceramic oscillator. Okay, we'll see that where it is available and all these things. So it can be enabled through the configurations. If you want, you can enable it, or if you want, you can disable it to the pin. Okay, and the next one is PLL. PLL, as I already said, it is in phase lock loop. Okay, it is present inside the microcontroller. Sources, you will be taking a source of an high speed internal or high speed external, and with that clock source as an input, you can perform the multiplication or division. Okay, so you can either multiply or boost your clock signal by using this PLL. That is what the use is. And we can enable this by using a pin configuration. Okay, so there are three different clocks available. Okay, so this is what an circuit diagram for external clock and your crystal or ceramic clock. Okay, and this is where your external clock is present. Okay, this blue color one. This X1 is your high speed external. Okay, and X2 is your low speed external, and HSC is an high speed external. Okay, here your high speed external clock is not available for the nuclear board. Only this low speed external is available, and high speed external is available for the ST link. Okay, I will tell what this ST link is in a bit. Okay, so these are hardware configuration that, okay, this I will show in the IDE. Okay, how to configure and all these things, everything. Okay, so this is your clock pulse and everything. Okay, this is an example. Okay, so this is a simple theory introduction about your ARM and STM board. Okay, so we haven't seen much about your STM boards. I'll show you how this STM board. Okay, uh, the STM board which we asked you to buy is an STM F446. Okay, if you want, you can buy, as I already said, F334 or F401. Okay, any board. Just a minute. I'm getting some message. Is it over here? No. Okay, no problem. Right. So what we are going to do is I'm going to download a data sheet for the board which I'm going to use. Okay. So depends upon your board. You can actually able to use the data sheets. Okay. So you need to download two things. One is your data sheet. One is your reference manual. We'll be using both the things in our module. First one is I'm going to use this 334R8T6 board. Okay. So I'm going to download STM32 F334 R8 T6 datasheet. So ST micro link. Okay, if I go over there, okay, you can see this STM32F334 R8 board. It is an Cortex M4 core architecture. It has a DSP and it has a floating point unit. Okay, so as I already said, your board itself, they will mention whether they are using what is this? Sorry. Yeah, your board itself they'll be using, or they'll mention whether they had an floating point unit enabled or not. Okay, and it is using an 64 kilobyte of flash memory, 72 megahertz of CPU, 12-bit ADC, okay, and 5 MSPs, and we have a comparator of PAMP, all these things. Okay, that is everything is same. So I'm just going to download the datasheet. This is for STM32F334 board. Okay, similarly, if you want, you can go and search the STM32F446R board. Okay, so again you can see this STM32F446RE. This board has an Cortex M4 core. It has a DSP and FPU. Okay, and it has a 512 kilobytes of flash memory, 180 megahertz of CPU. Okay, and it has an ART accelerated dual QSPA. Okay, so this is what actually varies from each and every board. This COM Cortex core is same. Okay, only the memory, how much CPU you can able to use. Okay, if there is any external peripherals you can able to use, which is available in this board, that is what going to matter, right? And again, it has an 12-bit ADC and all these things same. Okay, right. So you can download the datasheet if you want for this F446R8, and I think I have downloaded this one. Okay, both are same. Right. So now, okay, I'll just open this with edge. Okay. Okay. Now, as I already said, we have an M4 architecture Cortex M. Okay, Cortex M4. We have an microcontroller plus FPU. We have 64 kilobit of flash memory, 16 kilobit of SRAM. We have two ADCs, three DAC, three comparators and op-amp. Okay, and we have a 10 channel timer, high speed or high resolution timer. Okay, we will see what that all these things. So we have multiple features over here. First one, we can able to use it as an 72 megahertz of clock frequency. Okay, but your internal clock, it is actually in 8 megahertz only. Okay, we can able to use maximum 72 megahertz. That's what they are saying. Internally, you will be having only an 8 megahertz of clock frequency for your processor. Okay, maximum 72 megahertz you can able to use by using a PLL, right? So you can actually able to multiply it with 9 and you'll be getting something like in 72 megahertz of clock frequency by using this PLL. Okay. So these are your memories, 64 kilobit, 12 kilobits of RAM and everything. Okay. Now, so here you can see we have 51 different input output ports available. Okay. So we can able to connect up to 51 different input output devices, and all these devices can be mapped external interrupt vectors. That means imagine in your big microcontroller, we have only this RB0, that is an external clock, sorry, external interrupt. Correct? We have only connected our interrupt to RB0 and we have enabled our interrupt from RB0 only. Okay, but here we can able to use 51 input output ports, and all these 51 input output ports are external interrupt vectors. That means we can able to use 51 different external interrupts in this microcontroller. Okay, that much powerful it is. And apart from that, we have a 7-channel DMA controller. Okay, so you know about DMA, right? What is DMA?
Dynamic memory allocation.
No, not that one actually. Okay. So that will be very confusing because both the things.
Yeah.
Yeah, someone said, what was that? Yeah, Arvind. What it is?
Yeah, I'm trying to recollect.
Okay. So DMA, it will be very confusing because DMA is available in the C program. Okay, the as and dynamic memory allocation. Okay. But in microcontroller, DMA stands for dynamic memory. Sorry. Okay, DMA stands for direct memory access. Okay. So DMA is a direct memory access. We call it as a DMA controller. Okay. Now imagine we are having our microcontroller board over here. Okay. And we have something called as a flash memory inside this. And we have an peripheral device, any device. Okay. Now this peripheral device is actually going to store the data to this flash memory. That's it. A simple process, or it is actually going to retrieve the value back to the peripheral also. Okay, it is going to perform this operation, right? Now, what will happen is without DMA, I'm saying what will happen is your peripheral will send the data to your CPU. Okay, let's say this is your CPU. Okay, it will send the data to your CPU. This CPU will process it and it will send to the flash memory, and your flash memory will reply back to CPU, and your CPU will again transfer this to your peripheral. Okay, so this is what happened for each and every 32-bit value, because since it is a 32-bit microcontroller, your CPU can process 32-bit at a time. Okay, for each and every 32-bit, your CPU has to do the same thing again and again. So a value from the peripheral, it will process and it will send to the flash memory. Okay, but this is a simple data transfer between your flash memory and peripheral device, right? CPU is not even needed over here because we are not going to do any operation. We are just going to store that value in the flash memory, or whatever stored in that flash memory, we are going to retrieve it back to the peripheral. Okay, so there is no need of this CPU intervention over there, right? Now what will happen is, so instead of that, it is actually making your CPU more, heavy, or more process it has to perform unnecessarily. Now instead of that, what they did, they have made something called as a DMA controller. Okay, so this green color is nothing but it is a DMA controller, that is direct memory access controller. Now what will happen, instead of taking this path, now during this operation, your CPU will not perform any other calculations because it is quite busy with this data transferring, right? So it will not perform any other operation. Okay, that is actually very, wastage of memory and all these things, right? So now this DMA, what will happen is it will perform this data transfer. The name itself says is a direct memory access. So your memory will be directly accessed by using this DMA controller. Okay, so it is a specific controller that is going to perform all these memory related data transfers. What will happen? Initially, whenever the first data is transferred, it will just set a flag in the CPU. That is telling your CPU, hey, I'm going to transfer this data. Okay, it will raise a flag in the CPU. It will transfer all this data on its own to the flash memory, to the peripheral, all these things. Okay, once it is completed, it will again the flag which is raised in the CPU, that will be turned off or it will be resetted. Okay, that is we are intimating the CPU that I am doing some data transfer. I finish this data transfer. Only that signal will be transferred to your CPU. Okay, and your CPU can perform some other operation during that time where this DMA can transfer this data. Okay, that is what called as a direct memory access. So it will reduce your CPU usage, and it is increasing some other purposes also. Your CPU can do some other operations during that time, all these things. Okay, that is what your direct memory access. Okay, now here we have 7 channel direct memory access. That means we can able to perform 7 different operations at a time. Okay. And we have 2 ADCs. Okay, and we have an internal temperature sensor that is going to monitor your CPU temperature, and we have 3 DAC, 12-bit DAC, and here also we have something like a 12-bit ADC, I think so. Okay, so 12-bit ADC means it is 2 power 12, so that is nothing but it is an 2024 2000. Okay, it is actually 4096 different values will be there. Okay, so 0 to 4095 values we can able to perform. Okay, so the next one is we have, okay, these things are not necessary. Okay, we have 12 different timers available here in this particular board. Okay, so we have one 32-bit timer, one 16-bit timer with 6 channel, one 16-bit timer with 2 PWMs and clock and all these things, and we have a 2 16-bit timer with, okay, input capture, output capture, okay, output compare and PWM and all these things. And we have a 2 watchdog timer, and we have a SysTick timer, and 2 16-bit basic timer to drive this DAC. Okay, and we have an RTC. Okay, so apart from that, for the communication interface, we have a CAN communication. Okay, this is very important for the automotive, and we have one SPI communication, and we have one I2C communications. Okay, and then we have 3 USARTs that we can able to use it for the LIN and ERDA method, all these things. Okay, so these are the features of your board. Like we have 51 input outputs, we have 7 channel DMA, we have 2 12-bit ADCs, 3 12-bit DAC, 12 different timers. Okay, and then we have an RTC, and we have a CAN protocol, SPI, I2C, and USART. Okay, so these are the features of your board that we are going to we'll be writing the code for our driver codes for all these things. We'll be writing a driver code for GPIO. We'll be writing a driver code for ADC and for timers. In timers, we'll be using it for PWM mode, input capture mode. Okay. And we'll be using for the communication protocols, all these things. Right. So this is what your board and everything. So this is what your data sheet is. Okay, so if you go over there, each and every board will have its own data sheets and everything. This is what your architecture diagram for STMF334. So this is one of the very important thing you need to understand. Here we'll be having two different buses. Okay, so this STM board is having two different buses. One is APB bus, one is AHP. Okay, APB is an advanced peripheral bus. Okay, and this AHP is an advanced high-speed bus. Okay, some of the devices are connected in APB, some of the devices are connected in AHP. Okay, why this is matters is, as I already said, this is very important because if you want to use a specific peripheral device, you need to enable that specific bus. Okay, if you want to use any peripheral devices like I2C, SPI or CAN, anything, you need to enable this APP bus. Okay, if you want to access any GPIOs, then you need to enable this AHP bus. Okay, that diagram is actually given in this architecture. Okay, so you can see over here, this is nothing but your AHP bus. I'll just mark this in the purple color. This is your AHP bus. Okay, all your GPIOs, your ADCs, here you can see this ADCs, this GPIOs, everything is connected in the AHP, advanced high speed bus. Okay. Similarly, there are two different APB buses over here. One is APB2. This is your APB2. You can see, and this is your APB1. Okay, and in APB1 you can see what are the things are connected. It is timer 2, your timer 3, your user 2 and 3, your I2C, your CAN, and your DAC. Okay, all these things are connected, and your timer 6, timer 7, your watchdog timer, all these things are connected in your APB1 bus. Okay, there is one more thing in this APB1, that is this APB1 bus is 36 megahertz of clock frequency. That means you can actually able to allocate, or you can able to use maximum 36 megahertz of clock frequency for all these things like your timer 3, USART, okay, your I2C, can everything can able to use up to 36 megahertz only. Okay, whereas these on the left side, we have this external interrupt wake up timer. We have timer 15, timer 16, timer 17, timer 1. Okay, high resolution timer, SPI 1, USOT 1. All these things are connected to your APB2, and your APB2 is actually 72 megahertz of clock frequency. Okay, that means you can able to use your timer 15, timer 16, timer 17, timer 1, HR timer 1, SPI 1, USART, everything you can able to use up to 72 megahertz of clock frequency. Okay, so let's say by mistakenly in your program, if you allocate 72 megahertz for APB1, okay, all these devices will not work. Okay, so you need to refer your data sheet, this architecture diagram, like what are the things are connected to which particular bus and what is the maximum clock frequency for that particular bus. All these things we need to refer whenever we are writing the code. Okay, so that is what the thing is, and this is where your Cortex M4 is on the top. Okay, so this is all your devices will be connected over here. And there is one more thing which is very important, that is this one. Okay, your AHP and APB, that will be actually connected in this bus only. Okay, this common bus. Okay, we call this as a bus matrix. Your APB and AHP both will be combined over here and it will be transferred in this bus only. Okay, so apart from that, we'll be having this reset clock control. Okay, your reset clock control will be having all this clock over here. Okay, your APB clock, AHP clock, APB 1 and 2, then your frequency clock, F clock, H clock, USART clock, I2C clock, ADC. Your reset and clock control is the one that is going to allocate the clock pulse for all these buses. Okay, it is sole responsible for no, allocating the buses. So whenever you are going to allocate some clock frequency to these buses, you will be allocating via this RCC. Okay, so this is what an architecture diagram. This architecture diagram may vary to different boards. Like if you are using an STM 401 or 446, okay, most of the things will be same since it is an M4 architecture. Okay, only this clock frequency will get vary. That is the only difference between the multiple boards. Okay, so this is a simple introduction only. If you're not clear with all these things, whatever happened, no worries. Whenever we are writing the code, we'll be again discussing all these things over there. Okay, so no worries about that. And if you go to the bottom, you will see the pin configurations for each and every pins. Okay, what is this pin number and what is the function of that pin? Okay, all these things are given over here. And then this is the memory related things. Okay, like where your memories are, all these things, your code, your RAM, your peripherals, and all these things. Okay. This is done. Okay, apart from that, we'll be downloading and one more file, which is your reference manual. Okay, so just type STM32F334R8T6 reference manual. Okay, so reference manual is something different from your data sheet. Okay, so your reference manual will have something called as some thousands of pages. All the reference manuals will have a thousands of pages. Okay, this is like your data sheet of your pick. What you did in your pick, you'll be directly going to that particular register. You will be allocating that pin number. Okay, for example, if it is an RB0, okay, you'll, or let's say if it is an SPI communication, you will be enabling this SSP con 1, SSP con 2. Okay, all these things, right? Similarly, this reference manual contains all these registers informations. If you go over here, you can see, as I already said, you will be enabling the RCC clock for each and everything, right? So if I go to this RCC and registers, you can see this is an RCC control register for each and everything. For example, if you are going to enable the GPIO, okay, or AHP bus, you can see RCC. This is APB. This is APB1, APB2. Yeah, you can see this is an RCC AHP enable register. Okay, so you'll be enabling that particular pin or that particular register. Okay, for example, if you're going to use an port A, okay, then you will be enabling the 17th bit. Okay, that is an input output port A. This is input output port B. This is input output port C, port D, port F, and all these things. So this is for your SRAM. This is for your DMA. Okay, so this is for your ADC 12 channel enable all these things, right? So if you want to enable that particular thing, you'll be just allocating this clock pulse. Okay, and this is for your APB2. like all the timers, whatever we are shown in that architecture, we'll be enabling that particular register over here. Okay, we'll see one by one in our examples. Okay, no worries about that. So this is what the thing, and main thing is you need to download STM Cube IDE. Okay, so this one you need to download and install. While coming to class tomorrow, just install this one. This is a simple installation. There is no need to configure anything. Just download. You will have a zip file, extract it and double click next, select the location next and install. That's it. Okay. So search STM32 Cube IDE and open the first link. This is for your STM32 download. Okay. If you just scroll down, you will find something called as this get software. Let it load. Yeah. So once you got this, the last one is your STM32 Cube ID for Windows installer. Okay. Get latest. Just click it. It will ask the license agreement. Click accept. And it will ask to register. Okay. You can just simply click download as guest. Okay. But you required an ST account for generating the code in your Cube IDE. Okay, so for that, create account if you don't have. Okay, it'll ask something like the informations. You can give anything like what is the company name or university, what industry, what country region. You can give anything. There is no issues in that. But make sure your email ID and passwords will be as per what requirement they are given. Okay, so once you're given that, it will automatically download and extract that zip file and then install it. Okay, so once you install, you will get something like this. This is what your STM32 Cube ID looks like. I'll show what it is tomorrow. Okay, so this is how your STM Cube ID will look like. Okay. Right. So here only you just need to actually log into your STM because only if you're log in, then you can able to generate the code for the particular board. Okay. Since I already logged in, here it's actually saying hello Prasanna, my name, right? So once you successfully logged in, you will get this your whatever the name username you are given that will be over here. Okay, so make sure you have created an account in the STM and then logged into this STM Cube ID. Okay, so we'll be start working from tomorrow. If you don't have the board as of now, we will actually use this Workvi simulator. Okay, here you can see there is an STM32 board. Okay, but this STM32 board is actually, as I already said, it is an C0 board. Okay, so C0 board is nothing but it is an M0 architecture. If you want to go and download the datasheet, you can see STM32 C031. If I open this, you can see it is an M0 plus microcontroller. Okay, it has a 32 kilobit of flash memory, 12 kilobit of RAM. It has an 48 megahertz of CPU, 2 USART, timer, ADC, all these things. Okay, it doesn't have, I think, I think there is no CAN over here. I know that. Okay, it has one I2C, one SPA, and 2 USART. Okay, So also you can actually able to use up to 48 megahertz only using this crystal oscillator. So that is one thing. Okay. So if you don't have the board as of now, you can use it this work simulator for the device driver. Okay. But for RTOS, I'll say you need a board because in RTOS you can't able to do this with the C0 architecture. It is very difficult. It is not supporting most of the APIs from the free RTOS. Okay, so we can't able to use this workway simulator for the RTOS purpose. So anyhow, you have to buy this board for the RTOS. So get it now itself so that you can use it for both this device driver as well as an RTOS from now itself. Okay. So that's it for the introduction, right? So basics of the ARM architectures, this STM boards, and the installation of the software. Okay, so just download this and install. If you face any error while installation, okay, just let me know in my WhatsApp. Okay, I'll just guide you through this. Okay, clear? Okay, any doubts?
Sir,
Yeah.
I'm not able to order online the board. Today
Okay.
also I tried. It was showing error message. And one more website I found Element 14, and there also it was asking like GST number and all.
Okay. You can get it from the robo.in, I think.
Yeah, that only from that only today I tried. I
Okay.
was not able to. It is coming like error page after I select the payment method.
Okay.
Yeah. So the other website I found, but I'm not understand the configuration. Something is not available present in other boards like that.
Okay. Just search Nucleo 446, right? Okay. Nucleo
Mhm.
F446. You can get this with the robo.in.
Yeah, here only I'm having.
Mouser, they'll be asking it will be shipping from the US something, US or UK something. So they'll be asking some GST numbers and all these things for this one. Mouse electronics. You can get it from DigiKey also.
Okay. It
Okay.
will be same, sir, because I did not see same. The features was not same.
You can get it. See, this is an F334, so okay, 446R8. This
Mhm.
is again a nuclear 446R8. Okay, there's a difference between STM32 F446. Okay, for everyone, I'm saying this board, okay, which is different from your nuclear board. Okay, this is what your STM board is. This green color one. Okay, we'll be using nuclear board. I'll tell you what's the difference between this STM board and nuclear board. Okay, in tomorrow's class, but don't just search STM F32. Don't search that one. Search Nucleo F446R8 or Nucleo F 334R8. This one. Okay, get any one of this. So this
Okay.
one, I think it is 1800 in the
Yeah, this
robo.
is only when
Uh,
I'm checking, that
okay.
time it is showing error.
So this is actually 1200,
Hmm.
but they'll be shipping from the abroad, this DigiKey. Okay.
Yeah.
You can search this
So
also.
these both are same in the
No, same,
DigiKey and
same board, same board, same boards.
okay.
Okay. Mm, this is different one.
STM is different.
Okay, this is your STM32 F334. Okay, this is different. This is different. Okay, your nuclear
Okay.
board in the center you have this STM, this black color one. Only this is your STM one. That is this. Okay.
Okay. Okay.
If you
Okay.
want an entire board for this pins and all these configurations, then you need to get a nuclear board. Okay, search nuclear board. you will get one. Yeah. Any other issues? I hope no. Okay, so we'll see tomorrow. Okay, we'll start writing our first code and we'll work with this STM nuclear board from tomorrow. Okay, so before that, install that software and yeah, that's it. Install that software and come. Okay, so thank you. Bye. We'll see you tomorrow.
Thank you, sir.
Thank you. Bye.
Thank you.
Thank you, sir.
Thank you. Bye.
Yes.
Thank you, sir.
Thank you. Bye.
Sir, I have not purchased any board, sir.
Okay.
I will manage the money later and I will purchase it. Please guide me how to purchase it.
Yeah. Okay. Just let me know when you are ready to buy it. I'll guide it.
Yeah.
Yeah.
Okay, sir.
Okay.
Okay, sir. Thank you.
Yeah. Thank you.
Nice.